All right. So we're starting Unit 3 today. Unit 3 is consisting only of two chapters, Chapters 7 and 8. You can tell by the thickness of this booklet that Chapter 7 is pretty short. So we're going to learn about exponential functions in this chapter, and then that'll lead us into logarithmic functions. So you're going to see the connection between exponential and logarithmic functions, and logarithms have a couple uses. One of them being that logarithms will allow you to solve any exponential equation, no matter what the bases are. So we'll get into that. But first, we're going to analyze graphs of exponential functions, and then we'll look at problems involving exponential growth or decay. The graph of an exponential function, so it'll have the form y equals c to the power x. It is an increasing function when this base c is greater than 1. It is a decreasing function when c, the base, is between 0 and 1. So you can see the graph on the left is an increasing function because c is greater than 1. As long as the base is greater than 1, it'll be an increasing function. But when c is between 0 and 1, you get a decreasing function. So as it says on the right, an exponential function is a function of the form y equals c to the x, where c is a constant that has to be greater than 0, and x is the variable. So from the graph, you can determine characteristics such as domain, range, any intercepts, as well as any asymptotes. So we'll be talking about those. So in this case here, we're going to graph y equals 4 to the x, and then we'll talk about the characteristics, the domain, range, the x and y intercepts if they exist, whether it's increasing or decreasing, and the equation of the horizontal asymptote. So because the base c is greater than 1, we know this will be an increasing function. And we can sketch a graph by starting a table of values. So if I have x and y, and I can have both positive and negative values of x. So example, when x is negative 2, y will be 4 to the negative 2, or 1 over 4 squared, or 1/16. When x is negative 1, y will be 4 to the negative 1, or 1 over 4 to the positive 1, or 1/4. When x is 0, anything to the power 0 is 1. When x is 1, 4 to the 1 is 4. When x is 2, 4 squared is 16, and so on. You should realize that no matter how small x gets, y will always be positive. When x is negative 3, y would be 4 to the negative 3, or 1 over 4 cubed, 1 over 64. It's a decimal, close to 0, but still positive. And no matter how small x gets, as x gets smaller and smaller, the value of y will get closer and closer to 0, but it will always be positive. So because of that, the x-axis is a horizontal asymptote. The further you go to the left, the closer the graph will get to the x-axis, but it'll never actually touch it. We can plot some of these points. We have negative 2 comma 1/16, which is just above 0, negative 1 comma 1/4, which is a little bit bigger than 1/16. We have 0 comma 1, we have 1 comma 4, and we have 2 comma 16. Again, as we go to the left, the graph will approach the x-axis. The x-axis is a horizontal asymptote, and then the values of y will start to decrease. And you should also realize that it doesn't really matter what the base is, the x-intercept, the y-intercept will always be 1. Because no matter what the base is, anything to the power 0 always equals 1. So that's a sketch of the graph of y equals 4 to the x. Yes?
So why does 4 to the negative 2 equal 1?
Because 4 to the negative 2 is 1 over 4 squared. You have to make the exponent positive. So you move it from the top to the bottom. So there's the graph. The domain of this will be all real numbers from negative infinity to positive infinity. There's no restrictions on what x can be. We've evaluated when x is both negative and positive. The range, though, because the x-axis is a horizontal asymptote, it'll go from 0 up to positive infinity, and neither of those are included. Y will never be 0. It gets infinitely close to 0, but it won't ever touch it. And because the graph never touches the x-axis, there is no x-intercept. However, the y-intercept is at positive 1. And this doesn't mean that all exponential functions have a y-intercept of positive 1, because we're going to learn about transforming these graphs just like we've been transforming all our other graphs. If you vertically stretch this graph, it'll change the y-intercept. If you shift it up or down, it'll change the y-intercept. If you reflect it over the x-axis, it'll change the y-intercept. So the y-intercept isn't always going to be 1, because we can do transformations on these graphs. We can also shift it left or right. That'll change where the y-intercept is. Horizontally stretching it won't change the y-intercept, but most of the other transformations will. Okay, this is an increasing function because the graph shows us that, the table shows us that, the fact that the base is greater than 1 tells us that. And the horizontal asymptote, it says it's an equation, so you must have a variable and an equal sign. The equation of the horizontal asymptote is the line y equals 0. Right? So the only thing that changing the base will do, besides the fact that it changes whether it's an increasing or decreasing function, right? When the base is greater than 1, it's an increasing. When the base is between 0 and 1, it's a decreasing. But the other thing it'll do, it'll just change how rapidly it's increasing or decreasing. A base of 2 will look different than a base of 4. A base of 4, the values of y will get larger faster. So it's increasing more quickly than a base of 2. Okay? Same thing with a base of a half compared to a base of 1/8. The base of 1/8, it will decrease quicker. It'll still be decreasing, but just at a faster rate compared to a base of a half. Okay, so otherwise all those other things will remain the same. And so in this case, we want to look at the graph of y equals 1/2 to the power x. And we will do this by once again using a table of values.
Thank you.
You're welcome. Thank you. Okay, when x is negative 2, and we want to know what 1/2 to the negative 2 is, well, we would have to evaluate that by making the exponent positive again. If you flip the fraction over inside the bracket, that'll change the exponent sign outside to a positive. And so this becomes 2 over 1 to the positive 2, or positive 4. When x is negative 1, the same thing will happen. You'll flip the fraction over and get 2 over 1 to the positive 1, which is 2. When x is 0, doesn't really matter what the base is, anything to the power 0 is 1. When x is 1, 1/2 to the 1 is a half. When x is 2, 1/2 all squared will be 1/4, and so on. So when we plot these points, we've got the point negative 2, 4. negative 1 comma 2, 0 comma 1, 1 comma a half, 2 comma a quarter. Once again, the x-axis will be a horizontal asymptote. As x gets larger and larger, for example, when x is 3, 1 half all cubed would be 1/8, and then 1/16, and then 1/64, and so on. The values of y will continue to decrease, but they'll always be positive. If we let x equal negative 3, the answer will become positive 8, and so on. So this is our decreasing function, again, because the base is between 0 and 1. Once again, the domain is all real numbers. There are no restrictions on what x can be. Because the x-axis is our horizontal asymptote, our graph gets infinitely close to it but never touches it. We'll go from 0 to infinity for our range, but neither are included because it never gets to where x is 0. The graph will never hit the x-axis. Okay. Again, because the graph never hits the x-axis, there is no x-intercept. But there is a y-intercept, and that is at the point 0, 1. Doesn't matter what the base is, anything to the power 0 always equals 1. When x is 0, no matter what the base is, you'll always get 1 as the answer. This is a decreasing function. And the equation of the horizontal asymptote, once again, is the x-axis. It's an equation, so you have to have a variable, and you have to have an equal sign. It's got to be the line y equals 0. Okay? Thank you. So, if you're given the graph of an exponential function, you can write the equation. Okay? This is in the form y equals c to the power x. We need to figure out what the value of c is. And to do that, we're going to use one of the points that are on the graph. And the only point you cannot use will be the y-intercept, because all of these functions have the same y-intercept, unless it's been stretched or reflected or shifted, right? The last two examples we did, they had the same y-intercept, but they were completely different bases. So you cannot use the y-intercept to figure out what c is. The other reason for that is if you sub in the point 0, 1, you're going to have 1 on the left equaling c to the 0. Well, anything to the power 0 is also 1. You're just going to have 1 equals 1. C is going to disappear. You need to use one of the other points, which could be either negative 1, 4 or negative 2, 16. So I'll use negative 1, 4. X is negative 1 when y is 4. So we need to find out what c is. So to do that, I need to get c by itself. I need to get rid of the negative 1 exponent on the right. And I can do that by raising that to the power negative 1 as well. As long as I do the same thing to both sides, I haven't changed the value of anything. And on the right, negative 1 times negative 1 is positive 1. That's why I'm raising it to the negative 1. So I then get c to the 1, or just c equals 4 to the negative 1, which is 1 over 4 to the positive 1. And if you look at the graph, that is a decreasing function. So we knew that the base c had to be between 0 and 1. And now we see that it's exactly 1/4. And the equation of that function will be 1/4 all to the power x. If you use the other point, negative 216, you would have got the same answer. So just to show you that, y is 16 when x is negative 2. In this case, though, in order to get our c value, It'll be 1/4 as well, but in this case, we have to get c to the positive 1. So you have to ask yourself, what exponent do I need to raise the right side to, so that when I multiply the -2 by that new exponent, I get an answer of positive 1, and that exponent would be -1/2. You see, -2 times -1/2 will give you positive 1. So this will be c to the positive 1, or c equaling 16 to the -1/2. So that'll be 1/16 to the positive 1/2. And positive 1/2 as an exponent means square root. And the square root of 16 is 4. So you get the same answer for c. Took a couple extra steps. But again, this just shows it doesn't matter which point we use. The only one you can't use is the y-intercept to algebraically determine what the c value is. For this next one, that is an increasing function, so we know our c value has to be greater than 1. If we use the equation y equals c to the x to start with, again, we can use any point except the y-intercept. Can't use 0, 1, but we can certainly use 1, 5. And that is really quite easy because c to the 1 is just c. And so c equals 5. And our equation will be y equals 5 to the x. And that would work for that second point. When x is 2, 5 squared is 25. So you can quickly see that that equation works for the other 2 points. Yes?
For the negative one, question, if you not also, instead of putting times negative one, you also put it 1/c, and you evaluate.
Then what do you do to the left side? You have 1/c equals 4. So then what would you do? No, you're not asking me, would I? What would you do? So you've got c to the -1 equals 4. You went 1/c equals 4. How do you determine c?
Oh, switch.
What do you mean switch it?
You 1/c equals 4, then that would mean that 4 equals 1, or c equals 1/4.
How?
Over.
So this would work, but what you would have to do is you'd have to make both sides a fraction and cross multiply. It'll work. So then you'll get 4c equals 1, c equals 1/4. And as long as you can show that, yep, that would work. That would work. Now for the next one, it might not have been quite as easy, because you would have had c to the -2. Well, it would have worked. 1/c squared equals 16. You could have done the same thing. Cross multiplied and you would have got it that way. Yep, that will work. So remember, exponential functions have the form y equals c to the x. And if c is greater than 1, it models exponential growth because the function is increasing. When c is between 0 and 1, it models exponential decay because it's decreasing. So exponential growth is an increasing pattern of values that can be modeled by a function of that form, y equals c to the x, where c is greater than 1. Exponential decay is a decreasing pattern of values that can be modeled by a function of the form y equals c to the x, where c is between 0 and 1. So as we talk about problems involving growth and decay, specifically with decay, we're going to see the term half-life. It is the length of time for an unstable element to spontaneously decay to 1/2 of its original mass. How long it takes for half of it to disappear. So an application of an exponential function deals with radioactivity. A radioactive sample of radium Ra-225 has a half-life of 15 days. So every 15 days, there'll be half of what there was the previous 15 days. This also means that technically, it'll never completely disappear. There will always be a trace of it, because a half of something will always be something. It'll never be 0. So it's true that there would get to a point where the sample is so small that you may not be able to detect it, depending on what you're using. However, there will still be a trace of it there. So the mass m in grams of this radium remaining over time, t in 15-day intervals, can be modeled using the exponential graph shown. So again, if you look at the graph, the scale along the x-axis or t-axis is the number of 15-day intervals. So 1 means one 15-day interval. And that's why the mass that we started with was 1 gram. And then when t is 1, which is one 15-day interval, there's only half a gram because the half-life is 15 days. Every 15 days, there's half of what there was the previous 15 days. So 2 means we've actually gone 30 days now, and 3 means we've actually gone 45 days now. And each time, the mass remaining is cut in half. So the question A says, what is the initial mass of this radium in the sample? And the initial mass is 1. The graph shows us that. So that's the answer for A. The initial mass equals 1 gram. Also, part A asks, what value does the mass remaining approach as time passes? We would say that the mass approaches 0 grams, but it'll never actually get there, because half of something is always something. The domain and range of this function, because we're talking about an example that deals with a real substance, the domain would go from time 0 up to time infinity. Again, technically, it'll go on forever, always taking half of what there was. The 0 is included, the infinity would not be. And the range in this case goes from 0, which would not be included, up to positive 1, which is. Right? This sample starts with 1 gram. So that is the upper mass. The lower mass will approach 0, but it'll never actually get there. So there's part B. Part C says, write the exponential decay model that relates the mass of the radium remaining to time in 15-day intervals. So we're going to write the equation, starting with the general form y equals c to the x, and we'll use one of the points. I'll use the point 1 comma 0.5. That'll be the easiest one to use. So y is 0.5 when x is 1, and c to the 1 is c, and so that equals 0.5, which is a half. So our equation will be y equals 1/2 to the power x. And the reason it's a half is because the amount remaining is being cut in half. But we also have to remember that x refers to the number of 15-day intervals. Estimate how long it would take for the radium-225 to decay to 1/30th of its original mass. So let's look at the equation that we found out here. We have your equation, y equals 1/2 to the power x. What we want to know is how many 15-day intervals it would take so that you had 1/30th of what you started with. And with this equation, we can write a coefficient in front of the c. That coefficient would initially always be 1 times c to the x. And we're going to learn that that a value, because that's what it is, represents the initial amount. And that's another reason why it would be 1 in this case, because we started with 1 gram. Okay? Now, you cannot solve this equation algebraically. Can't do it. If we could somehow make the bases the same, and we will do some practice with that, because you did learn about that before, but that only works if the bases can be made the same, and in this case they can't. Okay? You could estimate using some logic, right? If we take t, which is the time, the number of 15-day intervals, and if we say that m, which stands for the mass remaining, as a fraction of what we started with, Okay, so we started with 1. After one 15-day interval, we'd have half of what we started with, or half a gram. After 2 15 days, that amount is cut in half again to get a quarter. After 3 15 days, the amount remaining is cut in half again. You're multiplying by half each time. You want to get 1/8. 4 15-day intervals, you'll be at 1/16. We need to get to 1/30th. And at 5 15-day intervals, we'll be at 1/32nd, half of what we were before. So we know that it'll take between 4 and 5 15-day intervals to get close to 1/30th, right? But we don't know exactly, or even can't even hazard a guess. Is it 4.6 days? Is it 4.7 days? What is it? Next chapter, when we get into logarithms, we will learn. We can use logarithms to actually solve this algebraically. And that's in chapter 8. However, we can use our graphing calculator to do this. If you go to y equals, and you put in there one equation as y equals 1/30, there's equation 1. Equation 2 will be the right side, which is 1/2 to the power x. Okay. Because our y1 equation is quite small, it's 1/30th. That's a decimal, close to 0. Because of that, I'm going to change my windows for my y minimum to -1 and my y maximum to +1. And I'll change my scale to 0.5. Because that first equation will be the line y equals 1/30, a decimal close to 0. I left my x min and max the same for now. We may have to adjust it. We'll see when we hit graph. So again, it drew the first graph in blue. That's the line y equals 1/30. And then it drew the graph of y equals 1/2 to the power x. We want to find the point of intersection here. Second function trace, number 5 for intersect, enter, enter, enter. So it's actually after x equals approximately 4.9. 4.906, 15-day intervals. So using the graphing calculator, we can get an answer, but it's going to have to be an estimate because this is an irrational number that needs to be rounded. In chapter 8, we'll learn how we can use logarithms to actually find it as an exact value. But for now, we're using the graphing calculator, and t is approximately 4.907. And that's the number of 15-day intervals. So if we take that and multiply it by 15, whoops, to get the actual number of days, it's approximately 73.6 days. Okay? The next chapter is logarithms. This chapter just deals with exponential functions. So here's an example of exponential growth. Under ideal circumstances, a certain bacteria population triples every week. This is modeled by the following exponential graph. What's the domain and range of this function? Well, again, this is a practical example. You can't have negative time. So it's going to start at time 0, which is the start of the experiment if you want, and it's going to continue on forever. That's why there's an arrow going up in this graph, right? The pattern continues. So the domain will be from 0 to +infinity. Zeros included. Infinity, no. The range goes from 1, which is included, up to positive infinity, which is not. Part B, we want to write the equation. And again, we can start with our general form, y equals c to the x. I'm going to use the point 1 comma 3. That is the easiest one to use. Because when x is 1, you'll get c to the 1, or just c equals 3. And if you think about it, the reason that c equals 3, because in this case, the population of the bacteria is tripling every so many weeks. In this case, every 1 week. Right? C will always represent the growth factor. In the last case, it was being cut in half, so the base C was a half. In this case, the number of bacteria is tripling. It told us that in the question above, and that's why the base would be 3, because it's tripling. C will always represent the growth factor, and A will always represent the initial amount, which in this case, once again, it is 1 bacteria. It starts at 0, 1. Okay, so our equation is y equals 3 to the x, and we may change the variables. Y is actually the number of bacteria n, and t is the time, or x is the time in weeks. So we might say n equals 3 to the power t, where t is the time in weeks. And w is the number of bacteria. Sorry, n, number of bacteria. Determine approximately how many days it would take for the number of bacteria to increase to 8 times the quantity on day 1. So for part C, we would have to graph y1 equaling 8, and y2 is 3 to the power x. And it doesn't matter which one is y1, which one is y2, that part doesn't matter. But we want to know how long it will take for the number of bacteria to increase to 8 times the quantity on day 1. Day 1 there was 1. 8 times that is 8. So that's why that first equation is y equals 8. So y1 equals 8. Second equation will be 3 to the power x. I'm going to have to change my y maximum here to at least 8. So maybe we'll use 10. And we'll set our scale back to 1 on the y-axis. And find the point of intersection. Second function trace, number 5 for intersect. Enter, enter, enter. So that's approximately how many weeks, because remember, it's the time in weeks. So t is approximately 1.89 weeks. And if we multiply that by 7 to get the number of days, approximately 13.25 days. Okay? All right, so tomorrow we'll look at transformations. We'll use the same rules and principles as we did, that we have been using since we started the course, learning about transformations. So you should work on those questions. I would encourage you to do those, do the practice. I'll post the solutions on Google Classroom so that you can check your answers. Okay? Sorry?